Good morning. I welcome you to this session. In the last class, we started the discussion on important thermodynamic property relations. We will do that in this class, continue that, just to started the discussion. So today what we will do, before going to continuing the thing that these property relations, thermodynamic property relations, we will just see two important, we will recapitulate two important mathematical theorem, very simple, which you know just as an information, we have to recapitulate. These theorems are like that. Let us see that if Z is expressed as a function of two independent variable x, y, this is a very simple mathematical theorem. Z is expressed as two independent variables x and y, then the total differential of Z, dz, can be written like this: del z del x at constant y dx plus del z del y at constant x dy. Well, now if I this coefficient I write as m and del z del y at x n dy, then it can be written that del m del y, that means the differentiation of this coefficient with respect to y at constant x is equal to del n del x at constant y. It is very simple because m is nothing but this one, del z del x at y. That means other way you can see that if we differentiate this with respect to y at constant x, what will happen? That means del m del y at constant x means the differentiation of this with respect to y, that means del square j, and constant x, that means this restriction will go, that means this del y del x. Very simple mathematical theorem. Similarly, if we write for del n del x at y, which means that differentiate this expression with x at constant y, that means this constant x restriction will go, that means this becomes is equal to del square z del x del y. And you know that if z is a continuous function of x and y, then these two double differentials are equal, even if the order is different. That means del square z del y del x is del square z del x del y. That means in any order the differentiations are taken, these second order differentiations, they are equal, provided z is a continuous function of x, y. So therefore, this is one of the very important relationships in mathematics which is used in deriving some important thermodynamic property relations. That if dz is expressed as m dx plus n dy, where m stands for the differentiation of z with respect to x at constant y, and n stands for differentiation of this variable with respect to y at constant x, then the differentiation of this with respect to y at constant x has to be differentiation of this coefficient with respect to x at constant y. Another important mathematical theorem is there which will be very much useful in deriving different thermodynamic property relations is this: if three variables x, y, z can be expressed as a functional relationship like this, that means x, y, z, three variables are dependent on each other and it can be expressed by a functional relationship of that, so that any of these variables for x, for example x, can be expressed as the function of other two. Similarly, y can be expressed as a function of other two, z as a function of other two. That means each one of these is related to the other two. That means if these three variables 1, 2, 3 are related by a functional relationship, so that one can be expressed as a function of the other two, then there occurs a relationship like that, a cyclic, this is known as cyclic relationship, that if you differentiate x with respect to y at constant z, then del y del z at constant x and del z del x with this at constant y, they equals to -1. So proof of this theorem is beyond the scope of this course, so I am not going to prove it because this is not a mathematics class. You have done it in mathematics class, but this information will be required. So similarly, just a immediate consequence of this in thermodynamic property relations, first I will tell that if XYZ is replaced by PVT, you know these three, pressure, volume and temperatures, are the basic properties of a system, basic, measurable and sensible properties of a system. Pressure and temperature are sensed also, and they are directly measurable properties. Sometimes we call these three are the primary properties, fundamental properties of a system, and they are related by a functional relationship for any system, which is known as equation of state. We will see afterwards that the relationship between pressure, volume and temperature for a given mass of a system, that means for a closed system, is known as the equation of state of that system. So therefore, an immediate application of this mathematical theorem tells us that del P del V at constant T into del V del T at constant P into del T del P at constant V is minus 1, which is again a very important relationship, because this is derived using this mathematical theorem for our thermodynamic property relations. Sometimes this is known as cyclic relations, del P del V del T and del T del P. So this is one of the very important thermodynamic relations. Well, now I come to the property relations which we started the last class, that we started with some four very important extensive properties. One is the U, that is the internal energy. Internal energy is basically the intermolecular energy, which neglects the kinetic energy, internal energy. Another is the H, that is enthalpy, which equals to U plus PV. Another is the F. What is F? F is the Helmholtz function, Helmholtz energy, or sometimes it is known as Helmholtz function. Helmholtz function or Helmholtz energy. Sometimes the concept energy comes because the units are all energy. That way enthalpy is also an energy unit, but this is not exactly an energy quantity. That you must know. So far you have learned this thing, because the difference of enthalpy gives the energy quantity, heat and work interactions in an open system. So enthalpy is very similar to the energy, whose dimension is energy, but is not exactly the energy. Similar way, Helmholtz function is like this. That's why sometimes it is known as Helmholtz energy, whose definition is U minus Ts. This is a system property. All these U, Ts are that of the system, because earlier we have seen that the availability function for a closed system is U plus P0V minus T0S. So there P0, T0 are the system, not surrounding, not the system, surrounding properties. Here F is U minus Ts. Similarly G, which is defined as Gibbs energy or Gibbs function, this is defined as H minus Ts. These H, Ts are all of system. That means they are all system properties. U, H, F, G. These four very basic properties of a system, where U is the internal energy, which comes from the first law. H is by definition U plus PV, and F, G, they come from the, actually this concept, physical what is that, physical implications or concept of significance of F and G. I told that this signifies the maximum amount of work that we can extract from a closed system when it interacts with the surrounding at an isothermal process, and the temperature of system and surrounding remaining the same. Similarly, when an open system interacts with the surrounding, an isothermal process where the temperature of the surrounding and the system remains same, then the difference of Gibbs energy gives the maximum work done. Similarly, the difference of Helmholtz function gives the maximum work done in closed system. So this I told you as far as the physical explanation or physical significance of Helmholtz function and Gibbs function is concerned. But at this present moment, it will be sufficient to know how these Helmholtz function and Gibbs functions are defined. Afterwards also, when we will start the reactive thermodynamics or thermodynamics of reactive systems, we will study this. In this course it is there, then we will be able to find out the physical significance of Gibbs function in more detail. So at the present moment, if we just recognize the definition of this four function this way, now I can write the differential form or an differential expression of this. du is TDS minus PdV. This relationship you know, TDS is du plus PdV, is a property relations which have been found from the first law of thermodynamics. Then I can write similarly dH, exploiting this, you see that du plus PdV plus VdV. Well, and du plus PdV is TDS. So therefore this becomes TDS plus VdP. Well, then next one I write dF is equal to, now you see here, if I use this definition, dF is du minus TDS minus SDT. So du minus TDS from here is minus PdV. So therefore this becomes minus PdV minus SDT. Similarly dG, if I write by differentiating this equation both these sides, so dG is dH minus TDS minus SDT. So dH minus TDS is VdP. So therefore this becomes VdP minus SDT. So therefore from the definitions of these functions I can find out, or I can write 4 expressions in terms of the differentials of all these properties U, H, F, G. Now they are the point functions U, H, F, G, and they are expressed in terms of differentials of other point functions ds, dv. Now in that case, in this case we can exploit this theorem. Now you see, this means that U as a function of SV, this equation tells that U as a function of SV, H as a function of SP, F as a function of Vt. That means if I start with U as a function of SV, then I can write du is, then in that case T is nothing but del U del S at constant V into ds. Then minus P is del U del V at constant S into dV. Similarly, if I could have expressed H as a function of SP, we could have expanded, or we could have written this expression. Similarly, F as a function of Vt and G as a function of Pt. That means this expression shows that these point functions are expressed in terms of the differentials of the other 2 point functions as independent variables. So therefore, we can now just have a recapitulation that as z is a function of x, y, and if it is written dz is m dx plus n dy, well, where m and n are these 2 coefficients which are like this, then one can write del m del y at constant x is del n del x at constant y. So therefore, exploiting that functional relationship from each of these equations we can write. Now we start with the first equations, u, that del t, be careful here, del t del v at constant s is equal to minus del p del s at constant v del p del s. Now here also you see that del t del p, here also from the second equation del t del p at constant s is equal to del v del s at constant p. From this equation we get del t del p at constant s is del v del s at constant p. From third equation what we get? From this equation both are negative, so we can write with positive things only, del p del t at constant v, del p del t at constant v is equal to del p del t at constant v will be equal to del s del v, very good, del s del v at constant t. From the last equation we can write del v del t at constant p, del v del t at constant p, del v del t at constant p is minus del s del p at constant t. So these are known as, these 4 equations are very, very useful thermodynamic relations, and they are known as Maxwell's, very good, Maxwell's relation, Maxwell's relations or equations, Maxwell's relations. They are known as Maxwell's relations. And at the same time we can write other few important relations by recognizing that when I write this u as a function of SV, then what is t? T is equal to del u del s at constant v. Can I not write this? Similarly, I can write what is p? P is minus del u del v at constant s. Then only you can write du is TDS minus PdV, means T is del u del s at constant v. and del u del v at constant s. Similar way I can write T also can be expressed like this. From this equation it is a function of s and p. So, this is del h del s at constant p. Similarly, v is del h del p at constant s. From here also I can write p is minus del f del v at constant t, and s is del f del t at constant v. So, in the similar way we can write v is equal to del g del t del p at constant t, and similarly s is equal to minus del g del t at constant p. So, these are del g del t at constant p. Also from these equations we can construct these relationships also. So, in deriving certain important thermodynamic relations, some of the expressions will be required. So, therefore, we can write all those equations from these 4 basics. That means, if we can express these 4 equations in this form, that's 4 basic functions, then we derive these equations. These 4 sets of equations are known as Maxwell's. This is the basic definition from which we wrote this, because this is del u del s v, this is del u del v s. So, that del t del v s is del p del s v. So, this is okay. Okay, please, third one, this one. Yes, please. Where is been minus? P is equal to this thing. Oh, say yes, yes, S1. These will be a minus. Okay, very good. There will be a minus. Very good. Then it is all right. Okay, okay. Now we will derive few other equations, important equations in thermodynamics, which are known as TDS equations, TDS equations. These are very important equations, you must know. So, today what I am doing, there is nothing much of thermodynamics in concept, which we discussed earlier, the first law and second law and their corollaries. These are more towards little algebra, primary level algebra rather than thermodynamic concepts, but we have to do it because we have to know the important property relations in thermodynamics. The other most important property relations that in thermodynamics are known as TDS equations. How they are written, just see that sequence of derivation. If I express now first TDS equation, now if I express S as a functions of T and V, let us express S as a function of T and V for a single component, single phase substance, S as a function of T and V. Then what we can write? We can write ds is del S del T at constant volume dt plus del S del V at constant T dV. And if I now multiply both these sides by T, then I get T del S del T V dt plus del S del V T dV. I can write the first term as Cv dt. Do you agree? The first term as Cv dt, T del S del T V. How? Yes, the question comes how, definitely. So, you cannot appreciate this. Now, Cv, what is Cv? Cv is some delta Q by delta T at constant volume when delta T tends to 0, per unit mass not, because it is the heat capacity, or if it becomes per unit mass delta Q by m, then it will be the specific heat. Okay, let us consider here heat capacity, because we are considering for the whole system, not per unit mass, all are extensive properties. Now, this we know that this expression we know that del dq is TDS, okay, del q by now TDS plus PdV. Now, at constant you see that du, what we know that du is TDS minus PdV, okay, and we know that delta Q is du plus PdV, this we know. Now, when we heat it reversibly with only work, because in defining specific heat there will not be any work except PdV, but at constant volume PdV work will be 0. So, del Q is du. Now, what is du? Du is TDS. Okay. So, del Q by del T will be du by del T is equal to TDS by del T, and that is at constant volume. That is at constant volume. That means it becomes T. This can be expressed at del S del T at constant volume. This is clear. So that T del S del T at constant volume gives you the value of specific heat capacity at constant volume, because small amount of heat delta Q is a change in the du, internal energy. So, del Q by del T is du by delta T tends to 0 at constant volume. This expression at constant volume when delta T tends to 0 becomes that del S del T. That means here delta T tends to 0 is del S del T. So, that is T del S del T. So, T is always there, T del S del T. Clear or any doubt? Clear? So, that T del S del T, okay, du again I am writing by delta T limit delta T tends to 0 at constant volume is T ds, here delta T limit delta T tends to 0 at constant volume, this becomes del S del T, T del S del T plus, now what is del S del V at T? Del S del V at T, now I come here, del S del V at T is del P del T at V, del S del V at T is del P del T at V, that is from Maxwell's equation. Sorry, one T will be there, you are correct, plus T del P del T at V, TDS. Any problem you ask me, this is mathematics only, there is nothing dV, very good, there is nothing to be excited, there may be some mistake, silly mistake, you can just detect me. This is the expression known as first TDS equation. This is known as first TDS. Clear? First TDS equation. CV dt in terms of T and V plus T del P del T V dV. Clear? Now, next we will derive the second TDS equation. This is first TDS equation, second TDS equation. Now, second TDS equation, second TDS equation is TDS is expressed in terms of T and P. That means, we start with S as a function of T and P, temperature and pressure. So, we can write ds, change in S, is del S del T at constant P dt plus del S del P at constant T dP. Well, so if we multiply with T, TDS is T del S del T at constant P dt plus T is there del S del P at constant T dP. Again, I can write this as Cp dt. Sorry, Cp dt. How? Let me again check how I can write this Cp dt. We know the definition of Cp is delta Q by delta T limit at constant pressure when delta T tends to 0. And I know that at constant pressure delta Q at constant pressure is nothing but delta H, rather I should write dH at constant pressure, that we have already know, because H by 1 the definition of H and del Q is d. This I am not writing again, this thing you know that the at constant pressure heat addition is the change in the enthalpy, because where from again still I am writing delta Q is d of U plus what is that PdV and d of U plus PV. One thing here you have to remember that whenever we define the specific heat of a closed system or specific heat of a system, specific heat is a property of a system. How do you define? This is very important. Here is the concept. These are very simple. I am telling you, throughout your life you will see mathematics is just a tool just to follow it, a little bit of merit will do. But what is tough is the physics, that is the concept. If concept is clear, everything is true. What is specific heat? Sometimes by the basic definition, we are not clear that when you define the specific heat of a substance, we consider a closed system comprising that substance. Then you add heat in such a way that there is no work transfer except a reversible work because of the system boundary displacement. That means we add heat reversibly through infinite small temperature difference slowly and allowing for no work transfer between the system and the surrounding except the reversible displacement work. What is reversible displacement? PdV work. So when you heat it at a constant volume, that PdV work automatically becomes 0. So absolutely there is no work transfer. So therefore always we write the first law as del Q is du plus PdV, because whenever I write the first law del Q is du plus PdV, probably in the examination, the class test you have seen, there are so many expressions and you are told under what conditions they are right. So del Q is du plus dW is the general statement of first law, no restriction, but del Q is du plus PdV, whenever I write this as first law, that means always we are assuming that closed system has work interactions only through reversible displacement work, that means PdV work. So therefore in definition of specific heat, we allow only PdV work. Therefore when you define the specific heat at constant pressure, we allow the PdV work to maintain the pressure constant, not by anything else. You cannot have any other work transfer to maintain the constant pressure. That is not the definition of the specific heat at constant pressure. Not that pressure will be held constant, will be held constant by allowing only the reversible displacement work. So therefore PdV, and when the pressure remains constant, this becomes this becomes dH. So this is again a recapitulation, because again and again if we recapitulate the basic things or earlier things, then your concept will be more or less clear. Now if we define this, now if with this if you write the expression Cp, then it will be simply coming as del H del P. So dH again we can write dH is TDS. Now a property relation VdP, because at constant pressure dP is 0, so that dH I can write ds. So del Qp is nothing but TDS at constant pressure, which means that Cp is by this definition del Q del T at constant pressure. T we can write in terms of the differentiation del S del T at constant pressure. No book will derive this when they discuss the TDS equations, I am telling, because they know that you should know these things from the very basic definition. So that you may be little confused that how they are substituting this, but I am doing it now. Be clear that T del S del Tp is Cp. And again the similar way that this expression, this should be here, that these expressions del S del Pt, del S del Pt is minus del V del Tp, okay, that del S del Pt is minus del V del Tp. So I can write minus T del V del T P dP, and this is known as the second TDS equations, and this is known as the, sorry, you better write it again, TDS, and this is known as the second TDS equations. This is known as, already I have written, second TDS equations. Now from these two TDS equations, I will derive a very important relationship. Now let us write the first TDS equation and second TDS equation side by side. First TDS equation is this one. This is the first TDS equation, TDS Cv dt plus T del P del T Vd. You just check it, I am writing the first TDS equation and second TDS equation. Let me write the second TDS equation first. TDS in the same place, TDS is Cp dt minus T del V del T P dP, whereas first TDS equation is this. Instead of that it will be Cv dt, it will be plus T, and this will be del P del T at constant V dV. You see that. These are the two TDS equations. Now if we deduct one from other, this from this, then we what we get? Cp minus Cv dt, this minus this, minus T del V del T P dP minus T del P del T V dV is equal to 0. Or we can write dt is equal to, okay, dt is equal to T, I write again and again, this will be better, T Cp minus Cv, these things if you take this side, del V del T P dP plus T by Cp minus Cv, well, del P del T V dV. Am I correct? You see whether I have done. So now I am writing dt is equal to T this side, other these two terms I am taking this side, T by Cp minus Cv del V del T dP plus T by Cp minus Cv. I am not taking this as common, T by Cp minus Cv, it can be written in that fashion, but I am writing in this fashion, del P del T V dV. Is clear? That means this term can be written as if, or rather we can write this way, dt is equal to del T del P, as T as a function of, by expressing T as a function of P and V, that means we can write del T del P at constant volume dP plus del T del V at constant pressure dV, which means that this term is equals this term must equal this, that means I can write this term, that T by Cp minus Cv into del V del T P must be equal to del T del P at V. Similarly, I can write T by Cp minus Cv del P del T V is nothing but del T del V at P. Clear? That means this term, this coefficient can be written as del T del P V, as if T is expressed in terms of P and V, and this coefficient can be written as del T del V at P. Simple mathematics. Well, now if from here we get Cp minus Cv is what? Cp minus Cv is T del V del T P into del P del T V, and the same thing we get from here. Cp minus Cv is T del V del T P and del P del T B. So that from both the equations we arrive, so equation is correct, we arrive the same expression for Cp minus Cv. Now you go back, well, any problem? Again I am telling, T is this del T del P V del T del Vp, because this is expressed T as a function of P and V. That means I can equate this with this one, well, and I can equate this with del T del Vp. Any problem? Simple, very simple mathematics, school level mathematics. So now if I just use this equation, del P del V, I want to substitute this. So del P del T is minus del P del T V, if we take this side, is minus del V del T P and del P del V T. That means I can write therefore Cp minus Cv, okay. Can you see all these three equations? You can see this, you can also see this, I think. Now if I use this cyclic relationship to replace del P del T at constant V by these two terms, then I get Cp minus Cv, there is a minus, minus T, now this becomes square, del V del T at constant V square into what is there? Del P del V at T. So this is one of the very, very important relationship. This is Cp minus Cv. That is, difference in heat capacities is minus T del V del T whole square P into del P del V T. Clear? Any doubt in anybody's mind? Is all right? Okay, now you see this term is always positive. The square of any real term is always positive. Now del P del V for all the substances are negative. Del P del V is always negative, which means that Cp minus Cv is always greater than 0, which means Cp is greater than Cv. Alright, Cp is greater than Cv. Clear? Now at this moment I gave you one example which may be told afterwards, or you know these things. Now this is a general thermodynamic relations. Now I can derive, or small relationships can be derived in terms of the characteristic parameter of a system if I know the equation of state. We know the equation of state is the equation between P, V, T. For example, in case of an ideal gas, for ideal gas which we will tell afterwards, the equation of state tells that P into V is m into R into T. For an ideal gas of a mass m, the equation of states tells that in an ideal gas the pressure of a closed system into its volume equals to m into R is some constant known as characteristic gas constant into T. So therefore in this equation, if we use this as equation of state and find out these parameters del V del T at P, then it becomes a very simple exercise. Del P del V at T, we will arrive Cp minus Cv is equal to mR. So we have to only find out del V del T at P, very simple. Del V del T at P, constant P is what? Del V del T at constant P is equal to mR by P. Similarly, del P del V at constant T, del P del V at constant T, you can find out what is del P del V at constant P. That means at constant T mRT by minus mRT by V square, because V you take del P del V at constant. So if we use these equations, then it can be shown that Cp minus Cv is m into R. This is a special case. That means if we have this equation between PVT, that means if we know the equation of state for different systems, then I can find out Cp minus Cv in a simple expression valid for that particular system. That means for an ideal gas, for particular system, then ideal gas Cp minus Cv is mR. But this is the basic thermodynamic relation. Now here another interesting fact we see that Cp is greater than Cv always, but there is a point where Cp exactly becomes equal to Cv when this becomes 0. When this will become 0, del P del V is never becomes 0 when del V del T becomes 0. So del V del T, for example, when del V del T becomes 0, when del V del T becomes 0, when del V del T at constant pressure is 0, Cp equal to Cv. And this is the case fulfilled by water at 4 degrees Celsius. Water at 4 degrees Celsius, del V del T at constant pressure is 0 because water reaches its minimum volume for a given mass, the minimum specific volume. So del V del T is 0. So these are few important relationships. Now after that I will tell you that there are certain definitions that we define beta known as volume expansivity. Volume expansivity, you must know, that is defined as, what is the definition? 1 by V del V del T. Probably you know that at constant pressure the change in volume with respect to temperature divided by the volume is known as the volume expansivity. Another expression is known as KT, that is isothermal compressibility. Now you know, already you have read it in fluid mechanics, that when you compressibility, when you compress a system, that means apply pressure to change its volume, the relationship between the pressure change and the change in volume depends upon the way which this change is brought. Whether that means that depends upon the process constant, whether the temperature is kept constant or not, whether the temperature is not kept constant, some other property is kept constant or not. That depends upon the constant of the process, because when the pressure changes, the volume also changes, other properties may also change. So therefore the relationship between change in pressure and change in volume, which defines the modulus of rigidity or the compressibility, depends upon the process constant. So two such process constants are very important. One is isothermal compressibility. That means if we change the pressure at constant temperature, then this quantity that means change of pressure with change of volume with respect to volume at constant temperature divided by the initial volume 1 by V. This is known as isothermal compressibility. That means change in pressure divided by the change in volume divided by per original volume at constant temperature. Similar is the case that if we make it isentropic. Yes, please, any question? No, isentropic compressibility. Sorry, I am extremely sorry. Del V, del P, del V. Compressibility with a minus sign. Very good, you are very thorough. Del V, I am extremely sorry. Otherwise, this reverses this the modulus of rigidity. Very good. Minus 1 by V del V del P, del V del P minus, because these are the scalar quantities with positive sign. Very good. And the reciprocal of these are defined as what is called modulus of rigidity. These definitions are very important. Now I will derive another one important relationship, that is the ratio of Cp by Cv. Now again, if I write the two equations, then these are all right. Now again, if I write the two equations, two TDS equations, you see that one is TDS is Cp dt, minus T del V del T at P dP, and the first TDS equation is TDS is Cv dt plus P, del P del T V dV. Now I can exploit these two equations to derive the ratio between Cp and Cv. Now if we consider isentropic process ds0, from here what we get? We get Cp is equal to, T del V del T at P, and this dP, then that will be del P del T at constant S, because I am using the constant entropy TDS, then this becomes 0. So dP by dt at constant S will be defined as del P del T S. This is clear? I can write from this equation at constant entropy, ds is equal to 0 at constant S, this equation. Similarly, I can write from the second equation, which is basically the first TDS equation, that Cv is equal to T del P del T V into del P del T V into del V del T S. Clear? With a minus sign. Yes, which one will be minus? Cp, this one will be minus. Very good. So therefore Cp by Cv will be what? T del V del T P into del P del T S divided by this, that means del T del V S into del T, T will be cancelled, I am sorry, into del T del P, V. This is clear? Del V del T P, del P del T S, del T del V S, del T del P V. So this can be written as these two together as del V del T P, there is a minus sign, I am sorry, and then del T del P V, del T del P del T V. Again del T del P V from the del T del P V, where is that? Del T del P V, del T del P, we can get this from, just wait. Oh, I have mistaken. Del T del P V, that there will be another term. Sorry, these two together, del P del V S, del P del V S, del P del V. Now first of all, we have to find out del P del V S. Del P del V S, where from you get del P del V S? Del P del V S. Just a minute. Del P del V S, we find out. Del P del V, no, we have to find out. Del P del V S is there. Del T del P V. Oh, sorry, I am extremely sorry. Del T del P V has to be replaced from the equation. Del T from the cyclic equations. I am sorry, this is not to be used. Let me call the cyclic equations. Cyclic equations, sorry, del T del P V, that means del T del P V, del T del P V, I use the cyclic equation, del P del V T into del V del T P, del V del T P. That means del T del P P is del V del T P. So therefore, I use this, this will be cancelled. So therefore, del V, that means del T del P, you see that del T del P V is, this is cancelled, del V del P, this will go there. That means minus 1 by del V del P. That means this becomes del V del P del V S divided by del P del V T. Clear? So this minus sign will go, because this del V del T at P, and del V del T P, this will be minus 1 by this, so this comes here. So I am replacing del T del P V from this cyclic equation. So this becomes equal to, as I have defined earlier, that the isentropic compressibility by isothermal compressibility. Well, so since Cp is greater than Cv, so this will be greater than 1, which proves that isentropic compressibility is greater than the isothermal compressibility. It's clear? Okay. All right. Now, I will start a very important aspect of second of thermodynamics is Joule Kelvin expansion. What is Joule Kelvin's expansion? So far we have discussed about the property relations. Okay, these were nothing but the mathematical relations, some algebraic things without any thermodynamic concept, much of any thermodynamic concept. Now what is Joule Kelvin expansion, which is very, very important, on Joule Kelvin effect, Joule Kelvin expansion or Joule Kelvin effect. Let us consider that a fluid is, while passing through a tube, is being restricted to flow by a valve. What is this physically? Let the tube and this valve are all insulated. You know the different types of valves are inserted in a pipe. The basic functions of the valve is to control the flow. That is known to everybody, even who does not have any much qualifications or have not gone through engineering studies. They know that if there is a flow of fluid, so if we have to regulate the flow in the downstream direction, we have a valve which gives a restricted passage. If the valve is completely closed, then the passage is completely closed, the flow cannot come here. So this becomes a static condition, the flow comes here, strikes here and exerts a pressure, there will be no flow here. As you gradually open the valve, that means allow the flow to take place, that means through restricted passages the flow starts taking place. Now in such a condition of a restricted passage opening, that means a partial opening or partial closure of the valve, when the fluid comes through this and flows through the valve, some at steady state some flow is maintained, then we know that pressure across this valve is dropped. That means there is a sudden drop or decrease of pressure across the valve. That means if one keeps a pressure gauge here, pressure gauge, let this section is 1, P1, and also keeps a temperature T1, and here if the similar way he keeps a temperature T2, this is the station 2, and keeps a pressure gauge P2. So if we place pressure and temperature measuring instruments at upstream, further upstream from the valve, so that where this stream is undisturbed, and again this downstream location will be where, will be at somewhere when again there will be no disturbance from the valve. So at a certain distance from here, where again the steady state is there, same flow is flowing through this, but we will always observe there is a decrease in the pressure. There is a decrease in the pressure P1. P2 is always less than P1. This process is known as throttling. Throttling. Throttling process. This is a colloquial term, engineering term used in shop floor, that fluid is throttled. Means the fluid is throttled means the flow is throttled so that there is a large difference of pressure. The fluid flows through this pressure difference. So flow rate is automatically reduced to take care of the frictional pressure drop. So this pressure is dropped because of the friction in the flow. Entire thing is adiabatic, that is insulated. Now try to understand the physics of this process. Now why the pressure is being reduced? Because of the fact that there is a frictional dissipation. That means pressure energy is being converted into intermolecular energy. So basically this is an irreversible process. But now the question comes, what will be T2? Will it be less than T1 or will it be greater than T1? Now the question, answer to this question is that this T2 may be less than T1, may be greater than T1 depending upon the situations which will be discussed. Why? That is because now you see that when the pressure is, there are two counterweighing effects taking place in changing the temperature from the initial to the final state. Now when there is a change in the pressure, now because of the friction, some of the pressure energy, the part of the mechanical energy is being dissipated into intermolecular energy or heat. So therefore what happens? The fluid temperature or the system temperature should increase. But at the same time when the pressure is decreased because of its equation of state, depending upon its equation of state, its temperature will also decrease. Because of a decrease in pressure, the temperature will decrease. So temperature will decrease because of a decrease in pressure. Okay, following its equation of state. We don't know what is the extent of decrease in temperature. That depends upon the typical equation of state. And at the same time, because of some fraction of the pressure energies, a part of mechanical energy being converted in intermolecular energy, temperature should increase. So these two countering effects decide that which one will dominate over others, so that there will be either an increase or a decrease in temperature. Under usual conditions, our common practice is that whenever you throttle a fluid so that its pressure is being reduced to allow it to flow through a restricted passage, usually temperature also drops, but it is not always the case. Now let us analyze this case by taking a control volume, like this, Now you tell me, what is this process actually? This is an irreversible process, there is no doubt, but we can write always the first law of thermodynamics or the conservation of energy for any process, reversible and irreversible process. Now if I write this in steady flow energy equations, at 1 and 2 flow is going out for this control volume, what we can write? Now steady flow energy equations we can write for unit mass basis. So we can simply write H1 is H2. Why? Because V1 is V2. Because the flow rate is same, the cross-sectional area is same. So if you recall the complete energy equations, we will see that H1 is H2 is the outcome of the energy equations, applications of the steady flow energy equations for this case. Because the change in kinetic energy is 0, change in potential energy is 0. So simply H1 is H2. There is no other energy interactions, neither heat nor work. So therefore this throttling process is an isenthalpic process, where the entropy of the process remains same. But please, enthalpy of the process remains the same. But one very important thing is that this process is an irreversible process, not a reversible process, so that the initial and final enthalpy remains the same. That means this process ensures the initial and final enthalpy to remain same, and it is an irreversible process. Now if I draw this process in TP curve, but immediately you must ask, sir, how can you draw a process in a thermodynamic coordinate plane if the process is an irreversible one? So I cannot draw this process. So therefore the question does not come. But what I can draw in TP plane, that if I go on varying this inlet condition P1, T1 at different values. No, sorry, if I am not going, sorry, I am extremely sorry. If I keep this P1, T1 fixed, but if I go on varying the position, that means the position of the valve, that means if I throttle to different pressures and temperatures, that means starting from fully closed position, if I go on slightly opening the valve, slowly opening the valve, that means that different valve settings creating different restricted passage areas which means that if I throttle to different pressure and temperature, if we do so, you will see that throttling pressure and temperature will be different. For the same initial condition, keeping the same initial condition, if I throttle at different valve settings so that I get different pressures and temperatures here, then I can tell that since the basic energy equation for this process is H1 is H2, I can tell all the values of enthalpy corresponding to different pressures and temperatures will correspond to the enthalpy at 1 which is kept fixed. That means I can generate the different state points with varying P and T, but with the same enthalpy. By doing so, and we can draw a curve which is nothing but the locus of an same enthalpy. You understand this thing? That means, and the curve will look like that. If I do so, the curve will look like that. This is an experimental fact. The curve will look, what is this curve? Let this point is P1 T1 and this is H is equal to H1 constant. That means by doing these experiments, I can plot different points on PT diagram, and this can be joined by a dotted line because this does not show a thermodynamic process. Rather, this shows a curve of same enthalpy. That means locus of equal enthalpy points. That means I can generate number of pair of P and T points whose enthalpy equals to the enthalpy H1, which is the enthalpy corresponding to the initial state P1 and T1. This is clear. And if we generate this way a number of pair of points with P and T having the same enthalpy, we can draw the locus of a constant enthalpy in TP plane, and this will look like that. That means this will first increase, have a maximum, and then it will decrease. Clear? So, this way we can generate a family of such curves if we now change this initial condition P1 and T1. If we change now initial condition P1, T1, that means we are going to a different enthalpy. Again at that same initial condition P1 and T1 set to a different enthalpy, we can throttle to different pressures and temperatures and generate again different sets of P and T values corresponding to this initial enthalpy. This way we can generate a family of curves which represent the constant enthalpy in TP plane. This we will discuss in the next class because time is up for today's class. Joule Kelvin expansion we will again discuss in the next class. Okay.